Alright, in this video I'm going to make a little foray into intermediate / advanced economics. What I'm going to do is something that you probably see some of in an intermediate micro class, but you don't really do a lot, everything that I'm going to do until maybe a master's or PhD level first micro economics class. But I'm going to do it a little more of a simple way than you would do it in a PhD level class. But what I'm going to do is look at demand functions and utility functions here. So I had a request come in to do this, and it's been a long time, but this is kind of fun for me to do. I'm going to look at Marshallian and Hicksian demand functions and where they come from, how you can derive them, using Lagrange multipliers, Lagrangian maximization and everything. We're going to look at indirect utility functions as well, and expenditure functions. So kind of the way I think about this, the way I was trained was using Hal Varian's microeconomic analysis book, 3rd edition, and so some of the terminology I'll be using is from him, but it's pretty standard. So nothing really really weird that I'm going to be doing here, but that's kind of a good reference is to look at chapter 7 from that book. But I know he has later editions out now. But here's a quick outline of what I'm going to do, and I'm going to do this very quickly. It'll take a few minutes anyway to do all this. I'm covering a lot. I'm going to just pick a particular Cobb-Douglas utility function here, and we're going to maximize it using Lagrangian multiplier and using a generic budget function here, budget line. First, we're going to derive the Marshallian demand functions for x and y. Then we're going to use those to derive an indirect utility function, which just makes a function that tells you how much utility you would get at the optimal level given what the prices of x, y, and the budget are. Then we're going to derive the Hicksian demand functions for x and y. And a Hicksian demand is called a compensated demand function. And compensated means that you're going to get more money as the price of a good goes up to compensate you to keep you at the same level of utility. And so we'll do that, and then we're going to graph and compare the Hicksian and the Marshallian demand functions that we got. And I'm going to put this, what I'm going to do is I'm going to use Maple, which is a symbolic algebra program, and I'm going to use Maple to do the math for us. So we're not going to get bogged down in algebra as we go here. And I'm going to post this Maple worksheet at www.berkeyacademy.com. You'll click on Files, and I'll call this Maple worksheet something like Marshall Hicks.mws, I think will be the extension. And it'll be a Maple worksheet that you can work along and change some things for yourself. So let's get started here. Here is, I'm going to need to move this a little bit so you can see everything. Just a sec. Okay, so here's the Maple worksheet, and I've got all the commands I'm going to use already here, and this is the way you'll get it. I can save a PDF of this with the answers as well. I'll do that. But if you want to use this in Maple, just go to the end of each line here and hit Enter. And I'll just briefly tell you what each line's doing so that you can know how to do this by hand and understand. So it's always a good idea in Maple to use the command restart. That gets rid of all the variables that might be left in memory from the last time you used it. And here we're just defining this utility function to be called u, x to the 0.3 times y to the 0.7. It did not recognize the structure's syntax. Sorry, I have an error here. Just a second. Okay, for some reason my Maple crashed, so we're back here. I hit Enter, and this just tells me that it executed the command. And then here's the constraint. Price of x times x plus the price of y times y is equal to some budget. And we could put in numbers for the prices in the budget if we wanted to, but we're going to leave these variables so we can get these demand functions out. And then here is the function that we want to maximize using the Lagrangian Multiplier method. U, our utility function, plus lambda, the Lagrange multiplier, times the budget constraint, but the way you put these constraints in is you make them equal to 0 by basically rearranging, subtracting this part from both sides, and you would move it over here so that it equals 0. So technically what you're doing here is you're adding 0 to this equation. So there's what our equation looks like. Now, what you need to do to solve this is take 3 derivatives, one with respect to x, y, and one with lambda. And that's what I'm doing right here. And I just name these equations 1, 2, and 3. You could name them practically anything. So there's our derivative with respect to x, derivative with respect to y, and derivative with respect to lambda. And I went ahead and set them equal to 0. And now what you want to do with these 3 equations is solve for the 3 unknowns. And so that's what I'm doing right here in this part. Solve 1, 2, 3 in curly brackets for x, y, and lambda. And then once we solve for the equations for x, that's going to give us the Marshallian demand, and y and lambda, this is going to assign those values, those equations, to be equal to x, equal to y, and equal to lambda so we can reuse them. So hit enter, and here is the equation for the Lagrange multiplier. Here is the Marshallian demand for x as a function of budget and price of x, and here is our Marshallian demand for y as a function of the budget and the price of y. A couple of notes here. For both of these, they're increasing as the budget gets higher. For both of these, the law of demand holds because as the price of x gets bigger, the amount of x gets smaller. Same thing with y. But one thing you don't notice here that you would typically think you might see is that the demand for x does not have the price of y in it. Now, if it did, the price of y could be in the numerator, meaning you buy more y when more x when the price of y goes up. That would make them substitutes. It could be in the denominator, which means they're complements. But it's just a side effect of the Cobb-Douglas style utility function here. That when you use a Cobb-Douglas utility function, the goods x and y are going to be independent goods. The price of one does not affect the amount of the other. So here's our Marshallian demand for x and for y. As I said, the function lambda here is also interesting because what it tells you is how much your utility will go up if you increase your budget by 1. In general, the Lagrange multiplier tells you how much the value of the equation you're minimizing or maximizing will change as you relax the constraint by 1 unit. So in other words, if we added $1 to your budget, this little equation expression here would tell us how much more utility you get for $1 more. If somebody gave you $1, how happy would that make you when you spent it on x and y? Now, how do you get to an indirect utility function? Well, the indirect utility function, we want a function of the price of x, y, and beta, and that'll tell us how much utility we get. Now, in order to get that expression, all we want to do is plug that in for x, plug that in for y into the utility function. And since I assigned those values, all I have to do is hit enter here and look and see what does the utility function look like right now. And that's it. So this is what we call our indirect utility function. And just a couple things to note about it. The b in the numerators says that as we get more budget, more money, we're happier. Our utility goes up. As the price of x or the price of y goes up, our utility will go down. And another thing that usually you talk about in micro classes when you look at an indirect utility function, is that it's homogeneous of degree 0 in prices and budget. What does that mean? Well, what that means is if we multiplied the prices of both products and your budget by the same multiple, say you get 10 times more income, and 10 times as the prices get multiplied by 10 times as well, then that won't change your utility at all. And you can see that in this equation, that if you multiply the top and bottom of both of these by 10, then the 10s will cancel, and it won't change your utility at all. Okay, so that's how you use the Lagrange multiplier method to derive Marshallian demands and derive an indirect utility function. Now, the next question that the person had for me in their email to me was this question: if I was given an indirect utility function, can I find the Marshallian demand function for x or y? The answer is yes, you can, and that's using a function or a relationship called Roy's identity. And Roy's identity says that the demand for x can be found this way. Take the derivative of the indirect utility function with respect to the price of x, divide it by the derivative of that indirect utility function right here with respect to the budget. And if you divide those two derivatives and multiply it by -1, because you're going to get a negative relationship there, then that will give you back the demand function for x. Now, instead of just asserting that, I'm not going to prove it. You can find the proof of Roy's identity in hundreds of textbooks out there. Well, maybe dozens of textbooks out there. Instead of proving it, let me just very quickly demonstrate why Roy's identity kind of makes sense. And I'm going to use some very fishy math here, so don't email me telling me that my math stinks. It doesn't, but I just want to do a little sloppy demonstration to give you some intuitive idea of why Roy's identity makes sense. Now, if we take, let me just simplify what we just have here and say x, just think about that as how much x you're going to buy, equals the derivative of indirect utility, so let's just say I, with respect to dp, the derivative of utility with respect to price, and that's all divided by this expression, derivative of indirect with respect to budget, so di db, that in this fraction, we can think about, and sometimes this is legitimately allowed in mathematics. I'm not going to worry about when it is or when it isn't. We can cancel that top change, the top change here of the change in utility, right? And in particular, it's if we're holding utility constant for people that are going to pick on me for what I'm about to do. But we can just kind of cancel those, right? And that leaves us with 1 over and 1 over. And so this is the numerator. This is the denominator of a fraction. And when we simplify that, what we get is the change in the budget divided by the change in the price. Now, how could that possibly give us how much x we're going to buy? Well, think about this experiment. What if I change the price by $1, right? So change the price by $1 or €1. Then how much will my budget have to change in order to give me enough money to buy the same amount of x? So we're kind of keeping the utility constant here. Well, if I add $1 to the price tag, how much more money do I need to buy all my x? Well, I need $1 for each x, so that's going to tell me how much x I buy, right? So if I change the price by $1 and I see how much your budget changes to let you buy the amount of X, the budget's going to change by how many X you're buying. Okay, so let's leave that alone. So you either kind of get what I'm going for there or not. All right, now, so let's use Roy's identity to get the Marshallian demand. Now remember, the Marshallian demand is this: 0.3b over the price of X. So let's just do it for X, the demand for X. We could do it for Y. So Roy's identity says take the derivative of the indirect utility with respect to the price of X. There we go. Take the derivative of utility with respect to the budget. Hit enter. There you go. And now we just want to divide one by the other and multiply it by -1. Why? Well, because this derivative is negative. It's always going to be negative. It just says when you change the price, your utility goes down. Right? And we want this to be a positive function for demand. So we hit enter. And we get this really ugly thing. But if we simplify it, what do we get? Well, we get 0.3b over the price of X, which is our demand for X. Okay? So Roy's identity allows you to take the indirect utility function. And why is it indirect? Well, it's indirect because it tells us indirectly, not how our utility changes when we consume more X or Y, but how our utility changes with the budget and the prices. So an indirect route to calculating utility. Okay, we're done with that. Now, the next question is, how would we derive Hicksian demand curves or compensated demand curves? Well, the Hicksian problem is to minimize your expenditure such that your utility is fixed at some level. We keep your utility constant, say at 10 utils. And so what we want is a demand function that's a function of that amount of utility, the price of X and the price of Y. So we're keeping your happiness constant. We're varying prices. And your budget's going to have to change to allow us to keep your utility constant. So here's how we do that mathematically. We set up a budget equation. Whoops, sorry, I have to restart here to get rid of those solutions we did before. Okay, so here's our budget. Price of X times X plus the price of Y times Y. And that's what we want to minimize. And here's the constraint. We have to keep your utility constant at some level U. So think of U as a constant like 10. So that's our constraint. So here is our function that we're going to use the Lagrangian multiplier method for. And we need to take 3 derivatives like we did before with respect to X, with respect to Y, and with respect to lambda. And then what we want to do is solve those 3 equations for 3 unknowns. And there's what we've done. Now this is really ugly, and often Maple will do this because Maple doesn't know, and sometimes it's important to know, whether these variables, U, X, Y, price of X, price of Y, whether they're real numbers, imaginary numbers, negative numbers. So it's using this root of notation. And when you see that, if you're working with positive and real numbers as we are, you can convert that to a radical. So that's what we're doing right here. Those are still ugly looking equations that can be simplified. So here I say simplify using symbolic means. That really means just don't worry about whether things are imaginary or negative. Just simplify it, not worrying about some of those picky details. And here are our simplified Hicksian demand for X, Hicksian demand for Y, and Lagrange multiplier. In this case, the Lagrange multiplier is going to tell us how the budget is going to change, because we're minimizing the budget here. How much will our budget go up if we change the constraint by 1 unit? In other words, the constraint is the amount of utility we have to get. And so this will tell us how much more money we need to get 1 more util if we plug a higher amount of utility into this equation here. Okay? Now, what I want to do is graph these two demand functions, the Marshallian and the Hicksian. Now first let's graph the Hicksian demand. Now to graph the Hicksian demand for x, let's just focus on that one. What I'm going to have to do is assume a level of utility and assume a price of y. So let's just pick, we want to keep this guy at 10 utils. Okay. Let's assume the price of y is $5. Okay. And let's plot that Hicksian demand function for x for prices of x from 1 to 10. And let's just see what we get here. Now keep in mind, I could reverse these axes, but here we have the price of x on the x-axis. So this is flipped from the way we usually think about seeing demand curves. But still it says that as the price of x goes up, the quantity of x goes down. And this is the Hicksian demand function. Now in order to plot a Marshallian demand function on top of that, what we're going to have to do is pick a price for x to start with. Now why? Well, because that Marshallian demand function, remember up here, for x, we need a budget. And for a Hicksian demand function, the budget changes all the time as the price of x changes. So we need to pick a budget. So we need to pick a price to figure out that budget for the Hicksian demand. So let's pick a price of 4. And at a price of 4, the Hicksian compensated demand would tells us we would buy between 6 or 7 units, I guess, here of x. And now let's figure out what budget we need to do that. Now, the easiest way to do that is to figure out what we call the expenditure function. The expenditure function tells us how much money we need to afford a utility, say of 10, at prices for x, various prices for x and y. That's the expenditure function. Now, since I use this little assign trick up here, it is assigned x to be this function and y to be this function. And when I plug those into the budget line, the budget equation, that's going to give me the expenditure function. And so here it is. It's ugly, so I'm simplifying it. Ta-da. Now this isn't really the full expenditure function, because a real expenditure function would be a function of the price of x, the price of y, and the utility level. This is a simplified version of the expenditure function because I told Maple to assume the utility equals 10, assume the price of y is 5. We could undo that and get the full expenditure function. But this video is getting long, so I won't bore you further. The reason I want to do this is to figure out how much money, what budget this person would need at this point, where the price of x is 4, and this plugs in a price of 4 into that equation, and it tells us this is how much money we need. To evaluate that as a floating point decimal number of ALF, okay, and it's going to be $86 and about 14 cents. Now, what this is going to let us do is plot the Hicksian demand function for x and the Marshallian demand function for x at a budget of $86.14 and compare the two, and then this video is going to finally end. And what you see is typical of the graphs you see in textbooks, but this is using some real numbers here, that at that price of 4, those demand curves cross. And they cross because the budget is the same at those 2 points for the uncompensated, the Marshallian, and the compensated demand function, the Hicksian, and figure out which one is going to be the Marshallian demand, the red or the green. Well, it's going to the Marshallian demand will be the green, because as the price of x goes up along the x-axis here, the Marshallian demand function will decrease more rapidly, because that is the function that where our income staying the same, the Hicksian function will only demonstrate the substitution effect and not the income effect, because we're compensating this person to keep them at the same income along the green line. So as the price of X goes up, we're giving them more money. So we're only seeing the substitution effect. And on the Marshallian one, we're seeing both the substitution and the income effect. Kind of neat, huh? So anyway, I will post this Maple worksheet on my website, www.berkeyacademy.com, and if you want to download it, it'll be called marshallhicks.mw or MWS. Just click on Files on the left-hand side of my website. And if you have any questions, please leave me a comment or question in the comment section below. I'll be happy to try to help. This has been a fun little adventure here, and hopefully we've all learned something. Good luck in your micro studies, guys.